When we talk about saving something to the cloud, it sounds like our photos and emails are floating around in the sky. But the reality is much heavier. The cloud is actually millions of physical computers packed into massive, highly secure warehouses. And here is where it gets interesting. Inside these warehouses, you might have a global streaming service, a major bank, and a massive multiplayer video game, all running their applications on the exact same physical machines at the exact same time. Think of it like a towering mega hotel. Tech companies don't usually build their own data centers anymore. Instead, they rent digital rooms, which we call servers, inside this massive shared building to host their businesses. Housing completely different, fiercely competing businesses under one roof is incredibly complex. Ensuring that the bank in room 101 never sees the data of the video game in room 102, while keeping the whole building running flawlessly, is the central engineering challenge of modern computing. In the early days of cloud computing, there was a catch to renting a room. To handle things like internet routing and security, the software managing the building actually had to sit inside the guest's room. This management software required its own slice of processing power, eating up nearly a third of the server's capacity, known as a virtualization tax. It also created a severe vulnerability. If the management software crashed, it took the customer's entire application down with it. Relying on software to manage the physical hardware created a stubborn bottleneck. It kept engineers from offering perfect privacy and maximum speed as the cloud grew larger. To fix this, Amazon Web Services realized they had to evict the manager from the room entirely. Instead of using management software, they built those networking and security tasks directly into custom physical hardware. They created the AWS Nitro System. All those management functions were moved onto dedicated microchips, physically integrated right into the layout of the servers. Because the management tasks are handled by a separate chip, guests now get 100% of the room's computing power. The chip also acts as a physical gatekeeper, locking the system down so tightly that not even cloud engineers can access the customer server. By offloading the work to dedicated chips, the Nitro system turned these shared servers into perfectly isolated, high-performance computing vaults. But what if your application doesn't need a massive permanent room? If you just need a computer for a fraction of a second, say to authorize a single credit card swipe, renting a full server and waiting for it to boot up is incredibly wasteful. To solve this, AWS built Firecracker. Instead of a full hotel room, it creates tiny, secure pop-up tents known as micro-virtual machines. Designed for extreme speed, they strip away slow startup routines, allowing a single physical server to launch thousands of isolated environments in milliseconds. Firecracker makes modern, instant response applications possible. It gives developers the strict security boundaries of a heavy, traditional server, completely eliminating the boot-up delays. Even the best servers are physical machines. Wires get cut, power grids fail, and bad code is deployed. How does the cloud stay online? The engineers looked to marine architecture. In a submarine, the hull is divided into separate physical compartments using heavy bulkheads. If a leak happens in one section, the bulkhead stops the water from sinking the entire ship. AWS applies this exact principle using cell-based architecture. They divide their systems into millions of tiny, independent clusters called cells. Each handles its own workload. If a bug hits one cell, logical walls contain the damage, preventing it from spilling over. By compartmentalizing the entire infrastructure, a severe local hardware failure is kept isolated. Your streaming service stays online globally because the damage is structurally trapped. There is one final piece to this mega hotel puzzle. How does the building guarantee that a guest's luggage, their data, is never lost or corrupted? They use a technique called erasure coding. When you save a file, it isn't stored as one solid object. The system mathematically slices it into multiple puzzle pieces. To protect against localized disasters, those pieces are scattered across completely different, physically separated data center buildings. Data survival in the cloud isn't about building indestructible hard drives. By distributing these mathematical shards, the system can instantly reconstruct your entire file, even if a whole building goes offline. When you tap an app on your smartphone, it feels instantaneous. But behind that single screen tap is a massive physical reality. Behind every modern app are heavy rows of computers, relying on dedicated Nitro hardware chips to guard the perimeter, Firecracker micromachines spinning up in milliseconds, and strict digital bulkheads trapping failures. These systems represent thousands of engineering decisions made to keep your data isolated and accessible. To see more of how this infrastructure actually works, subscribe to Refreshing Tech.